Hello, everyone. Welcome to class. So today we are going to have the second lecture that generalizes the idea that we developed the last time when we talked about the Diffie-Hellman key exchange. And remember that we looked at the algorithm itself, and then we distilled the very essence out of the algorithm, which is a discrete logarithm problem. And today we are actually going to reflect whether the two things are the same thing. So we are quickly reviewing cyclic groups and generators, and then we look into the discrete logarithm problem. We are defining it. And then we look into the Diffie-Hellman problem, and we ask the question whether the two things are the same. And finally, we generalize that idea of the discrete logarithm problem so that we can potentially develop other crypto systems. So finally, a look at the security of this fundamental underlying problem, the generalized discrete logarithm problem. We look at the attacks, and remember we were expressing security in the past in terms of bit length of the key. And we are going to do this here for this group of crypto systems again. So let's review real quick what cyclic groups and generators are. See the last week. So we had, for example, a cyclic group Z11 star, and it had 11 minus 1. So P is 11, and we had 11 minus 1 elements in that group, namely elements 1 all the way up to 10. And we have at least one primitive element, or what we called a generator, alpha. And the hallmark of the generator was if you put the generator to different powers, you can basically express any element in the group by way of alpha to the power of a certain exponent. So, which led to the notion of order of an element, and specifically the order of a generator, which is the number of elements that can be expressed. The order of a generator is actually the order of the group. So those two things are the same for generators. They are not the same for every element, but for generators, the order of a generator is the order of the group. And this is what this means here. Okay. So as a consequence, any element beta, any element beta of group like here, for example, Z11 star, can be expressed as a exponentiation of alpha. So in other words, as a consequence, for every beta there exists an x such that alpha to the x is congruent beta modulo whatever the p is. Here in this case it's 11. So for example, for our Z11 star group, we had a generator 2, and we developed a table to show that it is a generator. So we could show that for any x running from 1 through 10 followed a certain beta, and looking at all the betas that we generated, they were exactly all of the elements of the group as well. So 2 to the x, for instance, congruent 9 mod 11, in this case x would be 6, and you can look it up in the table that we developed last week. So a few things to note here. remember what we did with LFSRs. Those LFSRs, we needed to choose the configuration of the LFSR wisely so that we get a maximum period out of it. And what we do here is, and we called that corresponding configuration polynomial, we called that a primitive polynomial. And here in this case, our generator is a primitive element, so it takes pretty much the same role. And having the generator, we get a maximum period, if you want, so we can actually express all of the elements of the group by way of um, putting alpha to a corresponding exponent. So in order to generate all of the elements beta in the group, we have to run also through all of the values of such elements and put alpha to the power of such values in order to generate every possible beta in the group. So in other words, there is a mapping of group order x's, different x's, that map to different betas that are all elements in the group. So we map from 10 elements here in this case being x to 10 elements being beta in this example. But more generally, we choose from, we can choose from p-1 elements and put the generator to the power of such elements to generate all of the p-1 elements in the group, in the cyclic group. So in other words, that mapping is unique, it is unambiguous, and it is non-obvious. So unique, unambiguous, non-obvious. This is the important thing here to note, and something, for whatever the reason is not being made clear in many textbooks. Okay, so let's define what the discrete logarithm problem is. So given a p that defines our zp star and an element beta that is element of that group and a generator, the discrete logarithm problem is to find x such that alpha to the x is congruent beta modulo p. So why is it a logarithmic problem? Because solving for x, here being the exponent, of course leads to a logarithm, and it's a discrete logarithm because we also have the mod p here, which is something unusual what normally you do not see in logarithmic problems. Okay, so we looked already into an example the last time. I put it down here again to make, the mapping to show the corresponding parts, to show that mapping of the discrete logarithm problem to a concrete example. So here in this case, we have group Z 47 star. We have a beta of 41, and we have a generator which is 5. So the question here is 5 to the x congruent 41 modulo 47. So sorry about that. The question really is to find the x. And this is what we try to do. In this case here, brute force could lead us to find x to be 15. So the problem is how to find that x It's not obvious, given 41, beta 41, it's not obvious that the solution is 15. And so far, the only way how to solve this is actually through brute force. So what that means is that in a brute force scenario, remember that any x, and we have 46 such x's, maps to 46 elements. So what we need to do is we need to compute 5 to each of the values 1 all the way through up 46 and compute corresponding betas. And each time we do that, we get a different beta and see what the x is once we arrive at a beta of 41. So this is a problem to be solved here. Okay, so the discrete logarithm problem we derive from Diffie-Hellman, but let's reflect on the Diffie-Hellman problem itself and see whether the two are actually the same. And we can only speculate. We're going to see that we can only speculate about that. So see the Diffie-Hellman key exchange before. What is it that an attacker Oscar actually needs to do? And this is what the Diffie-Hellman problem actually is. So Oscar, eavesdropping the insecure channel, knows all of the information that has been sent over between Alice and Bob unprotected. So specifically, Oscar knows alpha, which is the generator. Oscar knows the P, which defines how many X's and how many betas there could be. So how many group elements we have. Specifically, we have P minus 1 group elements. And Oscar also knows capital A, capital B, which remember were the result of putting alpha to corresponding private keys that both Alice and Bob came up with independently. So we have a small letter A, we have a small letter B, and alpha to the A, small letter A, mod P is capital letter A, and similarly, alpha to the small letter B is congruent capital letter B modulo P. So this is how the information was computed at Alice's and Bob's sites. So of course, the attacker would like to know the shared private key that both arrived at independently, which, as you know, that key KAB is congruent to alpha to the power of small letters A, small letter B modulo P. So how can Oscar attack the system? So one way to solve this problem is, one way to solve the Diffie-Hellman problem is to solve the discrete logarithm problem. So in other words, knowing that that alpha to the A is congruent capital A mod P, Oscar would solve for the A and would arrive at this discrete logarithm congruence. Okay. So, and this is hard to do because of the modulo. Normally, to solve a logarithmic equation is very easy to do, but in this case, obviously, and unfortunately for Oscar, there's a mod P here, which confuses the whole solution of this equation. So if Oscar could solve for A and get the solution for small letter A, Oscar again could easily compute what Alice actually did. So what Alice did upon reception of capital letter B, that public key that Bob sent over to Alice, Oscar would do the same thing and put B to the power of small letter A, and that would equate to actually alpha to the small letters AB, and that would be the secret shared key. So the big question at a more abstract level now is the Diffie-Hellman problem, is that actually the same thing as the discrete logarithm problem? So which means is the only way to solve the Diffie-Hellman problem is to solve the discrete logarithm problem. And this is a big question mark. And it still is a big question mark. So unfortunately, we can only speculate whether that's the case. So it has not been determined yet. But experts see strong indication that these two problems are indeed the same problem. So in other words, there is no other way to solve the Diffie-Hellman problem but bypassing the difficulty of the discrete logarithm problem. So of course, an attacker would like to avoid that hardness and look for other ways how to solve the Diffie-Hellman problem. So not only tackle, the Diffie-Hellman problem by tackling the discrete logarithm problem, but maybe by some other way of solving this problem. So fortunately, experts in the field agree that most likely this is actually equal. So we seem to be in luck. Okay, if we can believe experts, and we probably should. So this is similar to what we have seen in RSA. So to this day, the only known attack to RSA is actually do prime factorization. And similar to Diffie-Hellman, remember that it was really easy. We could come up with two prime numbers and we computed n. And n was the product of such two prime numbers. So to do that multiplication is terribly easy to do, of course. While given n, it is incredibly hard to this day to come up with the prime factors, how n came to be in the first place. So we basically have a function that is easy to compute one direction, but it's incredibly hard to compute the other direction. So for RSA, at the present, we can, or scientists can compute and factor numbers up to 1,000 bits long. So that's the reason why the security recommendation for RSA is to go with at least twice the bit length. So you have seen that scheme before. So whenever an attack comes up that cuts down on our key length, what we do is we do not throw away the crypto system necessarily. What we do is we increase the difficulty to be so difficult again that it's unfeasible to solve the problem. So usually what is being done is that we make up by a factor the bit length by a factor to make up for the security glitch that could be shown by way of a certain attack. So this is what is being done here in RSA as well. And we saw that, when we talked about hashing as well, remember the birthday paradox basically cut the key length in half. So what we do is we just double it again. And that way we are again on the safe side. So it seems like a common theme that we have a security margin of twice of what reasonable attacks could actually do. So this is a recurring theme, and it also has to do, when you think about it, it has to do with future-proofing crypto systems as well. So a factor of 2 seems to be enough, apparently, to future-proof crypto systems. But of course, by and large, this is a moving target. So for RSA, however, when you compare what RSA is doing and the hardness of the function, being a one-way function, Diffie-Hellman is similar. It's incredibly easy to put the generator to a certain exponent and compute a result. This is easy to do, but it's really hard to actually figure out what the exponent was once you have only the result and the generator. So this is also a one-way function. It's just different in the semantics. So experts seem to be agreeing on that there is a higher likelihood that RSA can be solved in a different way than just trying to find the prime factors, the prime factorization as a brute force mechanism. Okay, so that said, we looked at the discrete logarithm problem, and it turns out that we can expand and generalize that idea and derive, by way of doing that, arrive at different, more sophisticated crypto systems. So we generalize the discrete logarithm problem to arrive at the generalized discrete logarithm problem. And this idea actually allows us to build other crypto systems that fundamentally rely on the idea of the discrete logarithm problem. So this is very interesting, of course. So the idea is that we use other cyclic groups than Z P star under multiplication to build other crypto systems. So, and the idea is that we have a group G, and this is what we did so far, basically, that every element in G can be expressed in terms of a generator that is being applied to operations of that group. What we did was we used exponentiation and multiplication to do that. But this is the very idea of the generalization, to not necessarily only consider multiplications, but other operations to generate each of the elements of the group. So that's the idea, and let's define that idea in more abstract terms. So given a cyclic group G, and it's unclear and at this point unspecified what the elements actually look like, and an operation donut, and again, we do not specifically define what donut actually is. And of course, that group has a certain order, and the order is n. And remember that for our prime groups or prime fields, actually, they were, when you think about it, they were actually prime fields, because a field is two groups rolled into one. We have a group under addition. This is the lower hanging fruit. And then we had groups under multiplication, which is the harder to fulfill requirement. And in order to make it work, we had to throw out the zero, remember? Um, so here in this case, we have cyclic groups that rely on different internal elements and on different internal and a different internal operation. So, but we have a certain group order here. So sorry for sidetracking. I try to rub certain aspects in so that you really know them. Okay, and then we have a generator, alpha. One of these elements, or possibly several, and we have a element out of the group beta. And the problem here is to be solved. Find an x which also has a value or used to have a value of the group, and this is not necessarily the case anymore. So find an x such that if we apply the operation to alpha a number of times, specifically x times, the result would be beta. Okay, so apply the group operation to the generator x times. And so alpha, donut, and so forth, x times, which would allow us to arrive at beta. So, and given the beta, that's the problem to be solved. What is the x? Okay, so when we look back, if we had a cyclic group under multiplication, we computed alpha to the x. If the group operation donut was multiplication with modulo reduction afterwards. So in a different scenario with a different group operation, we may actually have something like some sort of addition, and not necessarily what we mean by addition. So this is not necessarily like the plus that we are familiar with. So some sort of addition, and we can define addition to whatever it's going to be. In such a scenario, we would say that beta is being generated by, alpha times x. So, and this is exactly the case for elliptic curve cryptosystems, which we are going to cover in the last two lectures. So let's reflect in this context. Let's reflect what we have been doing so far and what we are going to do in the future to give you an outlook. So we have been looking into different groups so far. So groups theory is really important for cryptosystems, obviously. So lately we looked into ZP star under multiplication, which is actually a prime field. So we use that for Diffie-Hellman. Remember that we used a different field, an extension field, Galois fields actually. We use those fields in AES. And in the future, we are going to expand upon these ideas that we had so far with groups elements that are going to be points on an elliptic curve. And this leads to elliptic curve cryptosystems. And here we will define some sort of addition. So we're going to add points and basically have a cryptosystem that at its basis has the generalized discrete logarithm problem as its fundamental approach. So this latter part here is going to be the topic of our last two lectures. Okay, so now finally let's get to the very last topic for today. It's a somewhat shorter lecture. Let's look into attacks. So, and again, I mentioned that above, attacks basically define the key length of modern cryptographic systems. So the idea is that we look into a cryptographic system and we say, okay, theoretically, for a bit length of 80 bits, and 80 bits is a number that is, 2 to the 80 is so high that even that a brute force approach would not be able to go through all of the 2 to the 80 possibilities, options, and check all of them because the number is so ridiculously high that it's infeasible. And the next step to take is, well, what attacks do we have on our crypto system, and how is it going to affect the key length? And we saw that already with RSA. Prime factorization can be done up to 1,000 bits. And what we do is we double the bit size at least. So the security margin is obviously some factor. So if an attack reduces the key length by a factor, we make up by that and double on the efficient key length that the attack leaves us with. So this is being done here as well. So a brute force attack is, in the best of all worlds, a key length of 80 bits. That would be unfeasible. And now we look at attacks and see how much the attacks would eat away from those 80 bits. Okay. So there are indeed attacks on cryptosystems that rely on the discrete logarithm problem. So there are more efficient ways how to solve the discrete logarithm problems than just brute force. So there's a group of attacks which is called square root attacks, and there are two of them: baby step, giant step, and Pollard's row method. And unfortunately, they work on any group that relies on the principle of the discrete logarithm problem. So just imagine that. It's kind of surprising that if we derive other crypto systems with the underlying fundamental idea of the generalized discrete logarithm problem, that attacks are already there. And we don't even know yet what those crypto systems may be. So fundamentally, what these attacks do is they compute x in a square root of n steps. So which basically cuts the key length in half. So, and again, our standard response is to make up for the key length by the same factor. So what we do is here, we double the bit length to get the same security strength that we before had with 80 bits. So for these attacks, we are going to increase the bit length to 160 bits. So if you are interested, those two attacks, baby step, giant step, and Pollard's row method, are being described in the handbook of applied cryptography under these paragraphs, under these chapters. Not chapters, paragraphs, actually. Okay, so obviously these attacks are applicable to any crypto system that relies on the discrete or generalized discrete logarithm problem. There is a way more efficient attack, which is called the index calculus attack. It's more powerful, but only for certain groups. And specifically for prime fields, this attack can be applied, but it cannot be applied to elliptic curves, for instance, and groups that evolve out of the idea of looking at points on an elliptic curve and a corresponding addition operation. So, which is great because basically ECC systems, elliptic curve crypto systems, are immune to this attack, but normal discrete logarithm problems are not. So, with this attack in mind, we need to increase our length of p, the prime number that we have to choose. We have to extend p to a length of at least 1,000 bits. So, and if you again are interested in reading up on this attack, it's also in the handbook of applied cryptography under this paragraph. Okay. Alrighty, so that would be our journey from the Diffie-Hellman key exchange to the discrete logarithm problem. Compare this to the Diffie-Hellman problem and expanding upon the idea of the discrete logarithm problem to the generalized discrete logarithm problem with the potential to derive other crypto systems out of that underlying fundamental basis. So a very interesting journey. I hope you enjoyed it. Thanks for chiming in. Thanks for listening, and I see you in the next lecture. Bye.